Vm sine omega t. This is the AC source. Its value will be Vrms. How they are in series. What do you mean by series here? If the current across the elements, both in terms of magnitude and the phase angle, if it is same, then it is said to be in series here. So can you recollect the phasor diagram? Yesterday we have shown. So that phasor diagram is what we are going to take help of. And drawing phasor diagram is what the entire the AC this particular chapter is. Okay, let's assume now a current I will flow here. This current I will come here. So here it is having a phase angle 0. Will agree? 0 phase. Let's assume that one. Or some phase angle. Some phase angle it is. Then the same current will pass through this inductor also. Same current will pass through this inductor also. I don't know the phase of that current, some phase, let it be. Okay, let's come for this. Across resistor, will there be any phase difference? Nothing. So VR will be in the direction of current I only. Both will have same phase. Come for inductor, across inductor. Current lags the voltage, no? By how much? 90 degree. So therefore the VL will be like this. Able to make it out. So what is the phase of current? Is it phase of current 0? No. It is having some phase which I am going to determine here. I am assuming 0 phase for the voltage, applied voltage. You see that one. I didn't write any phase. Try to see here. Sine omega t plus. There's no phase here. So what is the phase of applied voltage Vrms? It is 0 phase. Like that you can think it. Or no sir, I'll assume current having some phase. Then the applied voltage will have some phase which we don't know, that we have to find out here. Is it okay? So now the phasor diagram, if you can recollect, I'll just make it. Either way, some books define either way. So this is something 0 phase, pi by 2, pi minus pi by 2. Anything which is directed horizontal should have 0 phase. Will I agree this? And anything which is having a phase difference of 90 degrees, it should be directed vertically. So now, so according to the convention, so let's assume that the phase of current, let it be 0. I'll write it nearby. What is the magnitude I and what is the phase angle of it will be 0 degrees. Will I agree? Then the applied voltage, I don't know its phase, that has to be determined. Books, I think they didn't, in the end they brought it, in the beginning only let it put. I don't know this phase angle, that has to be determined. Agree this? So either way, if you make this is 0 phase, then the current has to be taken some other phase. Why that phase angle will come later, you can see in the discussion part. So is it okay? No? When you can say two elements are in series in AC circuit, the two elements are said to be in series if the same current. Current means magnitude should be same and the phase angle should also be same. Fine. So there's a construction of any circuit comes, you should be able to construct using thing. Why VL? But sir, why can't you show like this? What's wrong if I think like this? Here current will flow here, high 0 phase. Because across the inductor open, current lags the voltage. No? So what's wrong if I show like this here? It's correct, no? Nothing wrong. We know across the inductor, current should lag the voltage by 90 degree. But look at this. I'll connect emitter one here and here. Both emitters will read same current and phase angle will be same. So this shows that the magnitude and the phase angle of the current should be same. Don't say direction, phase angle here. In mechanics, we say direction, vector, magnitude, direction. Here we say magnitude and phase angle. These are called like a phasors. Phasors, vectors. What happen? The physical quantities in mechanics will call them vectors. No. Here open in electric circuit, the voltages and currents are called as a phasors. They have some phase angle. SHM, phase angle, phase, initial phase, something we say, no, the similar thing here. No, so means like do we have meters which will indicate phase angle S? The ammeters what we construct now will also indicate phase angles. Now digital meters which are there. Analog cannot measure this phase angle. Digital meters will measure this phase angle also. Now look at this. Is it correct this circuit? It's a wrong. The reason for that R and L are in series. They should have same magnitude and phase angle. So therefore now this circuit is wrong. Now you have to be very careful about this particular thing. So this should be the correct one. So now let's write the diagram here. So I'll construct a diagram. So what is the diagram? The phasor diagram. Constructing phasor diagram is what numerical. Rest all you can see mathematics here. What is the phase of current? Phase of current is I. Next, what is the phase of? I'll call this as IRMS. I or IRMS. So let me call this is IRMS. What about the drop VR? VR will have a phase of here only. I just there's a VR. What about VL? VL is having a phase of 90 degree. So this should be the phase of 90 degree. So the vector VR, VL will be agree this. So the voltages are here. Vector sum of voltages we have to take. I'll shift this VL here. Now what about VRMS? Where the VRMS should come in between VRMS, and this is what that phase angle. Okay, got this. So now let's construct the triangle. So this is what voltage triangle it is called as. I'll take it out this. The voltage triangle will draw it. This is VRMS. This is VR. Why VR should have zero phase? I'm assuming current to be zero phase, and across the resistor voltage and current will be in phase. And this is what that phi. So let's define the things. What is the phase angle of the circuit first? First of all, is it VRMS? Shall I write? Is it correct? What these voltages are? They are the vectors. So we should do what? Vector sum of voltages. In AC circuit, so when you are writing out the potential drop, no, you have to take the vector sum of the potential drops. So this should be VRMS square equal to VL square plus VRMS square. This is a voltage triangle. Vector sum of voltages. I'm making clear. So what you should do?
VR square.
Sorry, this is VR square. So what you should do here now, in your bedroom, in bathroom, or on your hand, in notebook, okay, on dining table, or in the places where you are, and on nearby television, or to the mobile. Nowadays we have some notes, no, sticky notes. In AC circuit, vector sum of voltages has to be taken in series circuit. In parallel circuit, vector sum of current should be taken. Write that sticky notes. Daily see it 1 time, 2 time, 3 time, 100 time, 1000 times, 1 crore times. Daily you recite this. Vector sum of voltages in series, vector sum of currents in parallel circuit. Finish all. Rest all everything mathematics. Is it okay? No? So why? Because the voltages are treat voltages as vectors. Because if I say phasor also, you'd start thinking some other way. So let me call vector. No book has called it. For your convenient, I'm calling it. Anybody sees any other teacher, he will laugh. How you can call voltage as a vector? That one. If I say phasor, no, again you start thinking something VRMS equal VL plus VR. So let me write vector so that it will flash for you. It will get into your brain that VRMS square equal to VL square plus VR square, not VRMS equal to VL plus VR. But we should call that as a phasor. I'll write in the bracket. The phasor word is a correct. It should be they should be called as a phasor, magnitude and phase angle. Okay, let's go for the Ohm's law one by one. So what is Ohm's law for resistor? IRMS into R. What is Ohm's law across inductor? IRMS into XL. What is XL? XL should have the units that of resistance only, no? So let me substitute here. This is IRMS square, IRMS into XL. What should be the VRMS? VRMS should be again equal to IRMS into some quantity. I'll call that as impedance. So IRMS square will get eliminated. So Z square is equal to XL square plus R square. This is inductive reactance. This is a resistance. This is called as the impedance. And what should be the unit of all this? Should be ohm only. Inductive reactance. This is a resistance. The unit for all this should be ohm. Now let's write this. Let me construct a triangle again. So here I'm going to construct an impedance triangle. This is called as impedance triangle. Let's indicate the value. So this should be XL, this should be R, this should be the impedance. So Z square equal to XL square plus R square it is. Now if I write this in vector form, how XL is along pi by 2, no? I think if you go back to complex number, you indicated with a symbol what? High, no? Zero phase high. So here what happened, we'll indicate this by J. The pi by 2 is what? We'll call that as J. Minus pi by 2 as minus J. A phase angle of pi by 2, I'll give one specific. See, every time writing phase angle of pi by 2, I just call that specific angle. Phase angle is what? Will indicate by J. If it is having a phase angle of 180 degree, J square. What is the value of J square? J square will be minus 1. Plus J means phase angle of net, means an voltage is having a magnitude 10 volt, and I'll write J nearby it, or 10J. So what does it mean? Magnitude 10 and having a phase angle of 90 degree. If I write like this, minus 10J, having a magnitude 10 and having a phase angle of minus 90 degree. In vectors, what happened? There was no necessity of using this symbol. Here what happened? They're having some specific phase angle like 0, 90, minus 90, then 180 degrees. That specific phase angle will denote by a symbol. I think that is what happened for you in complex number. Here if I write it, this will be XL J plus R. So there I think there you use symbol I. So in the complex number, what do you mean by Z is equal to AI plus B? We say this is imaginary, this is a real, no? So what do you mean by imaginary? Which will not exist? Or there's a quantity having magnitude A and the phase angle 90 degree. What about B? It's a quantity which is having only magnitude and zero phase. And what about this Z? Z is a complex number. You say why complex? Because it's having magnitude and this one, and it's having a magnitude Z and having a phase angle that is given by tan of B by A, tan inverse of B by A. What do you mean by imaginary? You said imaginary axis. There's a real axis. Imaginary means, sir, which will not exist. No. Why? What is XL? XL equal to omega L. No. Go back all. What is XL? Is it omega imaginary or L is imaginary? Both are real. No. Inductor. So is it imaginary or a real device? Real device. No. You take a copper wire, make it like a spring. They'll become solenoid. It will have self inductance. So nothing called like a imaginary and real. Come out of the bookish world of mathematics. Complex numbers. Why you study complex numbers? Not to solve problem. Complex numbers are exclusively used in electrical circuits. Without that electrical circuit, we cannot solve. I cannot apply KVL, KCL, anything. I can't do that one. There's a major application of complex numbers. I think the maths, the way you studied was dry. So now, what is the thing like? You should know how to apply complex number at several places. So when you pick up electrical engineering, definitely open the complex numbers alone will help you a lot. Okay, any in JE Advanced in maths also they may ask you a very good question related to this because nothing is ruled out. Or in physics they may bring complex what all complex numbers what all you study can be applied here. So that imaginary axis, I think, please do imagine means which will not exist, nothing real, which is existing, imagine which will not existing. I think total stupidity here. But sir, why they call this as imaginary? Imagine if a quantity is having a phase angle 90-degree, it should be in this direction. The word imagine. So when you look at the complex number basic books, no, the statement has brought in that sense, and people started calling that y-axis as imaginary axis. A quantity which is having phase angle of 90-degree will be along imaginary axis. That's what the meaning of that. Okay, I'll come out of that. That I is called as the operator. No? So shall I call J as operator? So what is operator? J indicates phase angle of 90-degree. Minus J minus 90. J square 180 degrees. So there's a one representation and we do call this as now a phasor magnitude and having a phase angle. Z bar, if I call it, no, it is considered as a now a phasor, that one. Okay, let's come for that. There's an impedance triangle, voltage triangle. Now let's come for this phi. So what is tan phi? VL by VR. And now you have to ask questions. Are this VL, VR are they are RMS, instantaneous or maximum? Let there be RMS only. RMS value only. So VL equal to this will be IRMS into XL. IRMS into R. Further, XL is omega L by R. So the phase angle of circuit depends on what? Omega L and R means by varying frequency of source. Omega will determine the source. Omega depends on source. So I'll write it nearby. Omega by varying frequency of source, can I control flow of current? Yes, this is what the electrical engineer wants. Till now, what happened? You come across how to vary the. You go back to DC circuit. In DC circuit, what we did, how to vary the current. Tell me what are options for you. Either you should vary EMF of cell, or you should vary the resistance of the circuit. No, this was the thing. So now, without varying the EMF, without varying the R and L, can I vary the current? Yes, and varying frequency is very easy. How to vary frequency? Go for LC oscillation circuit. Can you vary capacitance? Yes. By varying capacitance, I can control omega. And by varying omega, I can control the current. By controlling current, I can control the power. So it is a new way of controlling power. What is that new way? By varying frequency of source, I can control the power dissipation in the circuit. There's a main theme of this AC circuits. In DC circuits, what happened? I should directly do physical changes. Where in the physical changes of the resistance, or I should do some physical changes in the cell to vary the current. But here what happened in AC source, just by varying frequency, one knob will be there. So is it that easy to vary frequency? FM radio, different channels, different stations, how you select by varying frequency. Is it easy or difficult? All of you, I think FM, you do listen, you do listen. How to select any station? Just by tuning, no, by rotating, no, it takes hardly a few seconds. So varying frequency of circuit is very easy. But varying resistance, inductance, capacitance, very difficult. Varying EMF, very difficult. How to vary EMF? Again, go back to Marshall EMF. How to control that EMF? Very difficult, no? So therefore, the engineers brought a method. They wanted certain method where they can control the flow of current by varying frequency. That's what this circuit is. This is the main theme of this AC circuits. Okay, got it, no? So I'm writing very clearly, the omega depends on source. This, if you vary R and L, current will change. It's no doubt that one. I'm not saying that if you vary R, current will not. R will change, but still more easier method is by varying frequency. Okay, no, I think some words you got J operator, impedance, all these things. So this called like a phase angle of circuit here. So therefore, what is this phi? I'll give one name. Phase angle of. All these formulas are very important. Then the whole chapter revolves around such formulas. Let's come for this. Now look at this circuit. Look at the applied voltage. What is applied voltage? VRMS. What is applied current? IRMS. So VRMS is called as applied voltage. What about IRMS? I'll call that as applied current. So now what I'm making? I'm making the current to lag voltage, no? Because say like, okay, this is a VRMS, that one. So compared to, or you can say voltage leads current. Since what happened, I'm going to take the voltage as reference. Then what happened, the current is lagging here. So therefore I'll give a name for this circuit. It is called as lag circuit. You should not change this. It's a convention. Everyone is following, you should also follow it. It's called like a lag circuit here. So current lags the applied voltage. So from where I think you can look at this one. If VRMS is having a phase angle of 30 degree, what is the IRMS? Having a phase angle of 0 degrees. I'll write that angles 0, pi by 2, minus pi, this pi. So definitely what happened, the current lags the voltage. So therefore this called like a lag circuit. How much it will lag depends on omega L and R. By varying omega, can I control this phase angle? S. This is the one advantage. Okay, this is about the lag circuit. How to obtain, can I control this phase angle? Yes, by adjusting L and R, or by varying omega, no? The phase angle is not fixed. It in fact is variable here. Okay, it's all about the circuit, you know. Let's go back to the power here. What about the power dissipated in the circuit? So what is the power? Already we know inductor will not dissipate any power, no? Will dissipate power only the resistor. So I want expression for power dissipation. Let's, I think I can't. Yeah, we have here only. So where all power, there's a power dissipated across the resistor. So for that, I'll do one thing. I'll go for instantaneous power first. Instantaneous power. Here I'm taking current as current lags the voltage, no? So here V into I. So what is V should be equal to Vm sine omega t plus phi. Im sine omega t. Is it justified writing sine omega t plus phi? Because current lags the voltage. So this should be equal to, no, Vm Im sine omega t, expansion of this sine omega t cos phi plus cos omega t sine phi. I'll write next step here. I think, okay, I'll take it out, I'll magnify it. Okay, try to look at this one. So we'll expand this sine omega t. Sine omega t cos phi into sine omega t. So further this ancient power Vm Im sine square omega t into cos phi plus Vm Im by 2 sine omega t cos. This will be sine. I'm directly adjusting it things. I adjusted 2 here for the second term. Then 2 sine omega t cos will become sine 2 omega t. And we have this much here. Okay, let's go for average of this. Because whenever power, average power, one for one cycle, I'll calculate here. Now, what should the average value of sine square omega t? 1 by 2. So this will become Vm Im by 2 cos phi. What should be the average value of this? Average sine phi Vm Im to constant. But what is sine, average value of sine 2 omega t? Will be 0. Whereas average value of sine square omega t will be 1 by 2. No, I'll write here. Average value of sine square omega t is 1 by 2. And so substituting all this and solving, so I ended up this much of equation. Got it now? So now further Vm Im by 2. Let's see that what actually it is. What is Vm? Vm by root 2. Shall I adjust this? Which is equal to Vrms IRMS cos phi. So this is the average power. You have to remember the formula at any cost. The average power dissipated in AC circuit is given by Vrms IRMS cos phi. Whatever the circuit, calculate that cos phi. How to calculate cos phi? This cos phi, I'll give a very good name. I'll call that as power factor. Cos phi is called as power factor. So this is, I think, the whole AC circuit. No, you can see that so many problems. 80% of numericals are related to this power factor only. It's oscillating only. What do you mean by oscillating here? So again, go back to AC circuits. What is the AC circuit basic idea? A varying current is flowing. The effective voltage is what Vrms. No, there's a major purpose of this one. Stick on to the basic things. I'll have water. Though varying current, varying voltage are there, but still what we'll express everything in terms of VRMS. That's what I think in the beginning we concluded here. Okay, I got this one. So let's go back to again that triangle. And now some regarding power I'm introducing. So there are, so let's plot that circuit. So this is the, oh, we know how IRMS is. IRMS is like this. No? Let's bother about only applied voltage and applied current. And what about VRMS? VRMS is, there's a phase angle of circuit. So can, and as I said, the applied voltage and current, they are vectors, no? So let me resolve component of IRMS along VRMS. Then what is the average power? VRMS into IRMS cos phi. So if I resolve, IRMS is having two components. One component along VRMS. How much it is? IRMS cos phi. There is another component IRMS sin phi. Which component of current will actually uh, responsible for the power dissipation? IRMS cos phi. What about IRMS sin phi? Will not dissipate power. So this is called like a Wattless current. This particular current, I'll call it as Wattless current. Now you should not laugh. So actually, which current is flowing? I, IM, IRMS, IRMS cos phi, IRMS sin phi. That's all, no? A student must ask really these three things, sir. What is this instantaneous current? That will vary sinusoidally. Maximum, RMS, RMS cos phi, RMS sin. Sir, among all, which currents are flowing? Actually, this is the current which is flowing. This we are expressing it in various ways. Okay, now this is the only current which is flowing in circuit. And what about IM? When it will be equal to IM twice in one cycle. IRMS is what the ammeter will measure. This is what responsible for power. This is what thing which is not responsible for power. We are just breaking up things. This is what actually flows. Actual flowing here. Getting the idea, no? No, component of IRMS will not generate power. Only IRMS cos phi is what responsible for the power here. This is called like a Wattless current. How to calculate Wattless current? We know phase angle. We know phase angle. How to calculate phase angle? Tan phi. Then this, how to get the power factor of circuit? Power factor of circuit, again, draw the impedance in the air. What is cos phi? R by Z. I'll draw once again that impedance triangle. Small things you ask yourself questions, it'll be on safer side. So this is the XL, this is Z, this phase angle, and this is R. That is what the ammeter, again, say ammeter is made up of resistor. No, the resistor will always measure the one which is responsible. IRMS cos phi it is. So what current flows, it will be generated, and proportional to it, it will measure. So you can't say ammeter to what it will measure. If a current flows, it will measure it. It will generate it. And proportional to it, the deflection will be there. And now what is cos phi here from the diagram? R by mod of Z, which is equal to root of R square plus XL square. Or further it is plus omega L whole square. Now, can I control power dissipation in the circuit? By varying omega. I'll shade only omega. R and L are fixed here because I don't want to disturb them. Varying R and L is a very difficult thing. varying omega is very easy. I'll just put a knob. So by varying omega, I can control cos phi. By varying cos phi, I can control average power. So like that, the power dissipation can be varied or can be controlled by varying the frequency of source. This is a major theme of this circuit here. So this power factor is something very important. You see that one. Why power factor? Now let's go back. What is the power factor for resistor circuit? What is
Infinity.
the, what is the angle between voltage and current? Will be 0. Cos phi will be 1. For pure resistive circuit, what is the power factor? 1. Then for pure reactive circuit, R will be 0, no? R will be 0. Then what's be the phase angle? The phase angle should be equal to how much? 90 degree. So what is the power? 0. So can I explain now the same inductor capacitor? Power dissipation is 0. The reason for that, XL is non-zero. In pure inductive circuit, XL non-zero. What about R? R will be 0. 0 by anything will be 0. So phi should be 90 degrees. Cos phi will be 0. Power will be 0. That one. So for power circuit, power factor R is 1 and for airline C it is 0. The value of cos phi will be 1 for resistive circuit, pure resistive circuit. For inductance and capacitance circuit, it will be 0. Emitter will read IRMS. In that open IRMS, cos phi is responsible for power dissipation. I'm making things clear. We can't separate IRMS cos phi, IRMS sin phi. Because what is the emitter? Emitter is having only resistance, no? So, okay, so what current is flowing across the resistor are IRMS only. Now let's come back to this one. So after getting this, let me break up things. I'm having all the triangles here. What is the power dissipated across resistor R? Should be equal to IRMS square into R only. Power dissipated, what is IRMS into R? In books, there's no much discussion on the power thing. Let me put in one simplified way here. What is IRMS into R? Should be drop across the resistor, no? Got this? This about VR. And what is VR? Let me draw the voltage triangle somewhere here. We have everything in front of. So what is VR? We can write VRMS cos phi. Is it justified? What all that average power? Who will dissipate here? Resistor and inductor is there. The only the resistor is what which will dissipate, which is equal to nothing but P average. So now, what is the average power? What is the average power dissipated in RL circuit? It is nothing but the power dissipated across resistor only. I just wanted to say that means if they ask you find the average power dissipated in RL circuit, calculate the current flowing through the resistor IRMS square into R. There is nothing but average power. Try to correlate things. Now, let's come for inductor. Across inductor, IRMS square into XL. No? This I'll break it up. What is IRMS into XL from Ohm's law? IRMS into VL. What is VL? We can write it as VRMS sin phi. This is not equal to average power. This is called like a reactive power. Call just Px. This is the reactive power. Then what we have one more, no? Total power dissipated in the circuit. Real power, and I'll call this as apparent power. Okay, let's go for, I can also write one more, no? Just only Vrms into Irms, that's all. This also lead to power, and this is called like a apparent power. Apparent power. So we'll give symbol P apparent. PS, right? Power supplied by the apparent power. This one apparent. The battery feels that is supplying this much of power, but how much is consumed? Only VRMS and remaining what across the inductor, and the inductor will return back, no? Then how all these powers are related? All this power. So the power triangle, now we can draw it. Px, this is PR, and this is apparent power. So then we can write one relationship. So now what is tan phi? Tan phi, you can also write it as Px by PR, reactive power by the real power. This is called like average power, or you can call it as, I think the word itself says real, reactive, then apparent power. The battery feels is supplying power of how much PS, but how much actually consumed? PR. Whatever the remaining is available across the inductor, and it will return back here. The battery, the cell will not see anything that O is there. It will supply this much of power. This is what really consumed, and the remaining output will be returned back. So therefore, this is called like a apparent power. It is. So like this, we have some, in books they avoided this possibility of asking in advance. Not in mains, at least in advance, definitely they'll ask you. So if they give reactive power and resistive power, from that we'll get phase angle. From phase angle, you can calculate the power factor, all other things related here. Okay, this is about all the conclusion. So what is a RL circuit? RL circuit is a lag circuit, which will make current to lag the applied voltage. And in this, who will consume power? It's actually only the resistor which will consume power. So it is not a dissipative power. Reactive power is not dissipative power. It's only exchange of power occurs between the source and the inductor. And what all the, when the cell gives any power to the resistor will dissipate it